Mr. Chairman, thank you for your introduction. Ladies and gentlemen, the title of my talk is a magnetic membrane actuator utilizing diamagnetic levitation. This work was done at the Institute for Microelectronics and Microsensors at the Johannes Kepler University, Linz in Austria. Our institute is dedicated to research on physical fluid sensors, miniaturized sensors for sensing physical fluid properties. And in this context, we are also doing research on microfluidic components and actuators. We'll start with an outline of my talk. First of all, I will tell you some words concerning our motivation. Then I will present the device concept, some words about the theory and simulation, the fabrication technology, then some experimental results with the first functional prototype, and I will end my talk with the conclusions and the outlook. So the motivation, what was actually desired at the beginning? We wanted to realize a membrane actuator in polymer technology. Electromagnetic actuation should be applied. And last but not least, the neutral position of the membrane should be adjustable without external energy input. So we came up with the idea to utilize diamagnetic levitation to stabilize the neutral position. This approach is compatible with polymer technology. It's fully passive and it's adjustable at least in the sub-millimeter range. The magnets are realized in composite technology, composite of polymer and ferromagnetic powder. And we use standard polymer, PDMS, polydimethylsiloxane, as the base polymer because its technology is easily controllable and it has several advantages for microfluidics. For example, it's optically transparent, it's flexible but mechanically strong, it's biocompatible and highly gas permeable, and it can be combined with a large variety of materials. Before I present the device concept, maybe some words concerning the phenomenon of diamagnetic levitation for those who are not familiar with this. Diamagnetic levitation originally denotes the effect of free levitation of a diamagnetic material in a non-uniform magnetic field. This phenomenon was discovered quite long ago. You see here it was first reported in the mid of the 19th century. And the picture here shows the free levitation of a piece of pyrolytic graphite. Pyrolytic graphite is one of the materials which shows the highest diamagnetic properties, at least at room temperature. And the non-uniform magnetic field in this case was realized with permanent magnets which are arranged in a chessboard pattern. A variant of diamagnetic levitation is diamagnetically stabilized levitation, which we actually used in our approach, and where diamagnetic material is used to stabilize the free levitation of a permanent magnet, which is shown in this picture here. In this configuration, a permanent magnet, this gold patterned cube in this case, is attracted by a lifter magnet, which is not shown in this picture, it's somewhere above, and floats freely above or between stabilizing diamagnetic materials. So here's the device concept. The magnets realized with a composite of PDMS and neodymium powder. The cylindrical floater magnet, which is shown here in the three-dimensional sketch and here in the cross-sectional view, is movable in vertical direction and is integrated in a thin PDMS membrane, shown here and this membrane here. The ring-shaped lifter magnet above is shown here and here, is embedded in the PDMS matrix, and underneath the floater magnet a piece of diamagnetic material, a pyrolytic graphite, is integrated, which facilitates the diamagnetical stabilized levitation of the floater magnet and hence also of the membrane. And for controlled actuation of the membrane, additionally, a coil is integrated in the PDMS matrix. Okay, maybe now some words concerning the theory of diamagnetic levitation. Looking at the potential energy of this floating magnet with a moment m in the magnetic field or flux density of the lifter magnet, it can be written as the inner product of the magnetic moment times the magnetic flux density plus a term for the gravitational energy. Z is the direction of the gravitational force and also the main direction of the magnetic field. Expanding the field magnitude of the lifter magnet around the levitation point in polar coordinates and adding two new terms which represent the influence of the diamagnet, one ends up with this expression for the potential energy. And now how it is possible to derive the conditions for stability based on this equation or based on this expression. Looking at the coefficients proportional to Z, one can see that at the levitation point, the magnetic field gradient has to balance the force of gravity. So this is the first condition for stable levitation. And then comparing the coefficients proportional to Z squared and R squared, one gets the conditions for vertical and horizontal stability. So at this point, I don't want to go further into details of mathematics. Especially, I don't want to show here now the evaluation of these coefficients ZC and ZR and CR. Instead, I would refer the interested listener to, for example, this publication where this model is actually nicely treated. What is important is that these conditions, the levitation condition and the conditions for horizontal and vertical stability, can now be used to run simulations to derive the geometric dimensions or geometric setup which fulfills these conditions. An example is shown here, a finite element simulation done with COMSOL multiphysics, showing the magnitude of the magnetic flux density for this configuration we are actually thinking of. Here's the ring-shaped lifter magnet and the cylindrical floater magnet and the diamagnetic material underneath. Once the geometric dimensions have been calculated, which fulfill the stability conditions, one can fabricate a functional prototype, which is shown here. We used this technology to realize the prototype with a polymer composite, and this was actually suggested first 2001 to use magnetically modified elastomeric materials for the realization of active microfluidic components. In this work, they actuated magnetic membrane with an external coil. We utilize a composite of neodymium and PDMS with different weight ratios and varying degree of magnetization, which offers the advantage that the geometric shape is variable and also the orientation of the magnetization can be chosen. For the neodymium powder, we use a powder which was designed for high magnetic flux densities and which features a grain size of 5 micrometer and which was obtained from Magnequench International Europe. And for the PDMS silicone elastomer, we used a standard product from Dow Corning. The functional prototype, the first functional prototype shown here on the right-hand side, was realized with a multiple-step PDMS molding process with final adhesive bonding of the single layers, except for the membrane, which is realized with a spin coating process. In this first functional prototype, the lifter magnet has already been realized as a composite, but you can see here in the middle from top view, the floater magnet is still commercial permanent magnet, a small commercial permanent magnet which was integrated in the membrane. So here are the first experimental results with this functional prototype. Doing the experiment, first the position of the lifter magnet has to be adjusted to achieve stable levitation of the floater magnet and also of the membrane. And the levitation height has to be kept well below the maximum achievable levitation height in order to leave enough room to move for the membrane without leaving the stable region. Then an AC signal with varying frequency was applied to the coil, and the maximum displacement right in the middle of the membrane was measured with a laser vibrometer. The figure here on the right-hand side shows here the measurement with this first functional prototype. It shows the normalized displacement in micrometer per milliamps as a function of frequency. And the two curves different with respect to that it's different membranes with differently sized magnets, floater magnets integrated. And they both show a nice resonance around 100 Hertz. So I'm already at the conclusion. We've shown the realization of a magnetically actuated membrane actuator where the neutral position was adjusted by diamagnetically stabilized levitation. The actuation of the membrane is induced by an integrated coil. The advantages of this approach are that the neutral position is stabilized with no external energy input as it was intended, and the separation of the home position of the membrane from the driving mechanism allows for many possible applications. And the next steps is the realization of the whole device in composite technology. As I said before, the floater magnet is still a commercial permanent magnet, a small one, and further miniaturization. In the end, I would like to acknowledge the Austrian Center for Competence in Mechatronics, which has partly funded this work. So thank you for your attention.